Okay. The very first thing, these are actually the mills that you'll be working on. Okay, so this is the lab. We have 5 vertical manual mills. So the purpose of this training class, or this class, is to help you to kind of, again, like the lathe, understand the basics of the mill, how to use it properly, what kind of accessories go with it, and what kind of tooling we can use on the mill. This is a slide worth taking note of, guys. Okay, so it is really important that you understand where the main parts of the mill are located and what they're called, just like we talked about on the lathe. At the very, very top here, that top arrow, okay, that top arrow right here, this is the head. All right, so just like the lathe, this is where the power is, guys. Okay, so the spindle is in, there's a motor up here, the spindle comes through, and what'll happen, the spindle turns, so this is a vertical mill, so the spindle is vertical, all right, it's up and down, whereas on the lathe is horizontal, right? And why we call the lathe the horizontal lathe is because the spindle is horizontal. This is called a vertical mill because the spindle is vertical. Okay, so this is the head. Okay, this is the spindle. This is the ram. So the ram, well, I'll just tell you the parts and I'll go into the detail of them. This is the ram here. The head is attached to the ram. The ram sits on the top of the column here, and the column sits on the base. All right. Now at the front of the machine, so this is a head, ram, column, base. This right here, this is our knee. Okay, so you'll see it down here, the knee. So this whole section right here is called the knee. The table sits on top of the knee. And then any work holding that you want to put on the table, in this case we have a vise sitting on the table. The table will move left and right, so that's your x-axis, left and right of the operator. Forward and back is the y-axis, okay, forward and back to the operator. And then the knee moves up and down in the z-axis. So the base is made of cast iron, okay? And in this case, this machine, the ones that you'll be working on, has a coolant reservoir so that you can run coolant automatically on your part. The base is usually one solid cast along with the column. They're usually cast together. Now, not always, but in this case, and as in many cases, the column and the base are cast as one piece. Now, over here on the right side, this is the machined face of the column. So just like on the lathe had ways that were ground and lapped to great precision so that the tailstock and the carriage could move linearly along those ways. The same is true of the knee here. The knee will move in a very precise way up and down these ways, or these ground ways on the face of the column. This is required if there's going to be any sort of repeatability in the movement of the knee in a vertical motion. The ram, as indicated here in the top picture. So this whole section right here, this is the ram, and it sits on top of the swivel. So you can actually rotate this ram 360 degrees. But the idea here is that the ram can also move forward or towards the operator and away from the operator because it also has this dovetail slide here. So this will have the male dovetail cut into it, and it will slide through on the receiving dovetail or the female dovetail. And then these are the locks for the ram so that it doesn't accidentally get moved or under tool pressure move away from or towards the operator. You can loosen these 4 bolts on the top of the swivel, and then you can swivel this ram circularly so that you can access more of the table or set up something off of the table. So you'll see here, that's the ram, the head's here. So here we see the head. Okay, a little bit more detail from the side. Here's our head. And the motor is mounted here on the top of the head. By means of this motor and a pulley system, it will spin the spindle, which is down inside here. I can also rotate this head, as you can see here. So I can loosen these 4 bolts right here, and I can swivel the head this way or swivel it this way so that I can create an angular cut on a piece of material. But just back here behind the head, right here on the front of the ram, see this right here? That's this. So I can loosen these 3 bolts and I can tilt the head down, or I can tilt it up, right? So it pivots around this pivot point right here, right? So these 3 bolts, if you loosen them, they will pivot around this center bolt here, so that my head will actually pivot and I can cut a different type of angle on it. So let's move ahead to the knee here. So this is, you can see here, the knee can move up and it can move down the column. You can also lock the knee. It's always a good idea to lock any axis that you do not want to move under cutting pressure. Okay, so there we go. Table is unlocked and moving, and in the last example we have it again locked so it can't move. All right, let's talk about just for a moment setting the tool height. Okay, so there's a couple of ways that we can do this. So first of all, the tool, okay, so let's say we want to use a drill. We can mount a drill inside this spindle here, okay? Now, usually what we'll do, and we have some other supporting videos for this, but typically what we would do is we would mount a drill chuck in the spindle. The drill chuck can open and close, kind of like a 3-jaw chuck on the lathe. It can open and close to take a variety of sizes of shank of a drill, so that we can put in whatever drill that we need so that we can cut a feature on the surface of a workpiece. But when we go to put any sort of tool, whether it's a taper shank drill or a drill chuck, what we're going to do is we're going to put it up inside the spindle here. We're going to tighten this drawbar. So this is a bar that goes through the head. So that is up here. It goes through the head and it has a threaded end on it. So any tool that we mount up in the spindle will have a receiving thread. And so as we tighten this bolt, it will draw it up inside the spindle, hence drawbar. As we're tightening this bolt, we don't want the spindle to turn as well. So we will pull down on the brake right here. If you pull down on this brake, then you can tighten this drawbar and pull the tool up inside. Once the tool is mounted inside the spindle, we want to know exactly where the contact point of that tool is on the workpiece. That's our 0 position for our tool. So if I put my drill in here and there's a workpiece sitting on top of this vise, I want to bring my tool down and touch off the top of that workpiece, and down here I want to set my 0. So I would rotate this collar to 0 so that once I bring the spindle back up, it doesn't matter where this spindle is. I can set this on the knee as my 0. And then I can move the knee up or down to my tool. So if I move past the 0 in the Z positive position, whatever this reads is going to be the depth of my cut. An easier way to understand this is with the DRO, or the digital readout. So I can actually bring my in some cases, this one is only an X and Y, but there are ones that have a Z readout. So I can bring my spindle down and then just hit Z0. And then anytime I move this quill handle up or down, it will indicate here where the quill is. So I know when I'm approaching 0, I know where I'm going away from 0. This DRO is also very useful for the X and Y axis. So I can set a piece of material on here and create a datum or a 0 position. Because on a print, typically all features that need to be cut will have a dimension related to a start point or a datum. So I can set that datum in the DRO, and you'll get more experience with this once you get into the lab. This little item here on the side, this is your quill stop. So if I wanted to drill a hole, so this lever, this is my hand lever for my quill. I can bring the drill down into a piece of work and then bring it back up again using this handle. But if I want to go an exact distance, I can either set this stop down, say 1 inch. So I can set this 1 inch. This is the top of the stop. I can spin this nut down 1 inch away from here. And then when I pull this lever down, this stop will hit this threaded nut wherever I set it. So this will travel down and hit it, and that will stop the drill wherever I set it. So I can use the quill stop in this handle to drill a hole, or I can leave this handle up and I can lock the quill and then bring the knee up into the drill. And that's where I would use this graduated collar. I'd set my 0 here, and then I'd raise the table or raise the knee into the tool, and then this graduated collar would turn as the table's being raised and tell me how deep I am cutting. There's some different types of work holding that we can use on the mill. So here's just a few examples. Up here, we've got a step clamp set. They have little grooves in them, little steps, so that you can set them up like this. So this is an example of using a step clamp set. So you would put this end over top of the workpiece that you want to hold down to the table, and then you would tighten down this nut, and it would put pressure here. Now there is some pressure that's obviously going to be here as well. So we'll talk a little bit more how to properly use the step clamps. The vise is the most common piece of work holding that we'll use on a vertical mill, but there's other options. This is an angle plate. An angle plate would be used in conjunction with maybe some clamps or something else, but there are lots and lots of options. Even 3-jaw chucks, just like on a lathe, we can take the cam bolts out of the back of a 3-jaw chuck and then set that 3-jaw chuck down flat on the table and use it to hold round work as well. There's other accessories that we can use, and you'll get an opportunity to use hopefully some of these in your apprenticeship, but most definitely in the working world, you'll have an opportunity to do some more advanced setups. So in this first picture we have over here, so you can see what we've got set up. We call this a dividing head. So on the left side of this video, the work is being held in a dividing head, and on the right side in this video, back on this back side, is the tailstock. So the dividing head, basically what it is it's a mechanism that allows us to rotate a part just like on a lathe, but it doesn't rotate constantly or under power. We rotate it into a position and then make a cut along the length of the work, and then rotate it to the next position and do the same. So this video here is a video of us cutting a long gear that we will cut into pieces later. Up here, we have an example of a compound angle plate. So we showed an angle plate in the last slide. It was just like a precision ground backing plate almost. It sits flat on a, designed to sit flat on a surface plate. And then the front is ground perpendicular to the bottom. So that is just like a solid angle plate. This is a compound angle plate. So I can actually create the angle I want. Rather than have a 90-degree angle, I can set a 45-degree angle. On this compound angle plate, I can create a compound angle. So not only can I set a 45-degree angle in one axis, I can set a 15-degree angle in a second axis, allowing me to cut more complex angles or drill complex angular holes. We also have a couple other options here. There are many more options, but these are a little bit more typical of more advanced work holding. So this is a rotary table. So this rotary table would mount onto the table of your mill, and you would mount your part onto the top of the rotary table, and you can use a dial indicator, which your instructor will show you how to use, and indicate a part so it sits exactly on the center of this table. And then as you spin this hand wheel, this table will rotate. So you can cut grooves and features on the exterior of a part. You can cut flats, you can drill holes, you can do all kinds of things. Here's a 4-jaw chuck mounted on the top of a rotary table, right? So this is another type of rotary table, so it ends right there, and then the 4-jaw chuck sits on top. We talked about order of operations for the lathe. So we, obviously there's a proper order of operations or a manufacturing process for the mill. So one of the things that we want to state, but we also want to make very clear, when we put a tool in a spindle to create a feature, it is good practice to create multiple features. For instance, if I need to cut 4 holes with the same drill, it's a good practice to cut all 4 holes while that drill is installed. But there's no one rule, and that isn't always practical because if we needed to counterbore that same hole, so if we had to center drill and then drill a hole and then create a counterbored surface on that hole, personally, my preference would be to put the center drill in, come down and center drill the hole, then throw the drill in, and then without moving the table or anything else, follow that center drilled hole with my drill. And then once that hole is drilled, take the drill out, put the counterbore tool in, and counterbore the hole, all without moving the table. For me, that's my preference. But again, there's no one rule. Each job will kind of dictate what seems to make the most sense. But a good rule to remember is that the order of operations or the manufacturing process should always lean towards never cutting away work that you've just created. So in this example of this block, notice that this material at the top, so this would have been one solid piece of material, and we've cut all of this away. We've cut this slot, we've cut this groove, these 2 holes. It wouldn't be good practice to take this raw block and drill a hole all the way through and then cut away this step, right? Because we've just cut a hole all through here. Why did we cut that hole if we're just going to remove it with another tool, even if it's just to leave some of the hole behind? So it's always good practice to think about your order of operations and never remove a feature or a portion of a feature that you've just created. That's generally frowned upon. And so just like we had in our lathe demonstration, I try to consider which features I need to cut, what the best order would be for cutting those features, and then I create a tool list to accommodate those features, right? So tool number 1 Notice order of operations. I want to square up all the sides of this block. I want to make this block perfectly square to start. Well, I'm going to choose a tool that will allow me to do that. So in this case, I'm going to choose a 3.5 inch face mill. And then of course, each feature that I want to create will have an associated tool set aside so that I'm ready to cut that part in a proper sequence.